The receiver operating characteristic, a graphical representation from the confusion matrix, which only works, unfortunately, for binary classifiers and has a rich history. So remember, we have these three extreme classifiers. So totally positive, everything's positive. Totally negative, everything's predicted negative. Or coin toss, label observations using the toss of a fair coin. So in that case, the little p is 1/2 the positives and little n is 1/2 the actual negatives. Now we'd like to avoid these extremes. These aren't good classifiers. These are edge cases that completely ignore what's in the data itself. So let's look at the true positive rate and false positive rate. Well, if we have a totally positive classifier, then the true positive, the false positives are equal to the negatives, and therefore the true positive rate is 1 and the false positive rate is 1. If it's totally negative, then true positives and false positives are both 0, so the true positive rate is 0 and the false positive rate is 0. So we can visualize this relationship between true positive rate and false positive rate. We put the true positive rate on the vertical, the false positive rate on the horizontal. Both go from 0 to 1. And the ideal would be a true positive rate of 1 and a false positive rate of 0. So we put the green dot there at the 0, 1 point in our plot. The extremely positive classifier is at the corner where you have 1, 1 for true positive rate, false positive rate. The extremely negative case is the origin. And coin toss is right there in the middle, 1/2, 1/2. So remember, this point at 1 on the y-axis, that's the ideal. Now let's suppose we had an extremely random classifier. So this means we have a coin and we have a probability of heads of q. Then the true positives are q of the positives and the false positives are q of the negatives. So using very large data sets, we have the true positive rate is q and the false positive rate is q. And that means we have this point QQ. For example, if Q is a fourth, or if Q is 0.9, and notice these form a line between the two corners of this unit square. And that line, anything on that line we say is a random classifier. So above the random classifier, the true positive rate is greater than the false positive rate, and below, true positive rate is less than the false positive rate. So remember, we've got the random classifier is this vertical line, true positive rate equals false positive rate. And the ideal is in that corner where we have 0, 1. But in reality, we'll probably only ever get very close to that corner. So let's use some notation. Little f is the false positive rate, little t is the true positive rate. And so we've got this point close to but not exactly equal to the ideal with the coordinates ft. And we can connect the corners of the random classifiers to form a curve. And this curve that goes from the origin through this ft up to the 1, 1 point is called the receiver operating characteristic. The name comes because it originated in World War II in its use in analyzing radar and radio communications. Now let's look at the area under the ROC curve. The region under the ROC curve is the union of a triangle and a trapezoid. So let's find the area of the triangle, which is 1/2 ft, and the area of the trapezoid is 1 minus f times t plus 1 over 2. And therefore we get this expression, which becomes t over 2 plus 1 minus f over 2. Now recall that specificity is 1 minus the false positive rate. So the area under the curve is the sensitivity plus the specificity over 2. It's the average of the two. So it's 1/2 of the quantity, true positives over positives, plus true negatives over negatives. Notice if P is approximately n, then the total number of observations is 2P, and therefore the area under the curve is TP plus TN over the total. Now if P is approximately n, the area under the curve therefore is the probability that an observation chosen at random is classified correctly. In general, the area under the curve is the probability that a classifier correctly differentiates between a randomly chosen pair, one positive and one negative. In other words, if we chose two observations, knowing that one was positive and one was negative, the area under the curve would be the probability that the classifier got them right. So a predictive model predicts probabilities that an observation is positive. So let's look, for example, at the tunable binary data with a 5 nearest neighbor classifier. We're going to go to 1,000 points in the training and testing sets, and again here n equals 4. And we're going to predict the 5nn probability that xy is labeled positive. So here's the actual. You can see those predictions of positivity are actually numbers between 0 and 1. So we can use the receiver operating characteristic because the actual is either 0 or 1. The predictions are between 0 and 1. So again, the predictions are between 0 and 1. And we can use the ROC to help select a number called the threshold. So the threshold is a number between 0 and 1 such that predictions above that are labeled positive and predictions below that t are labeled negative. So what is the best value of t? Well, first you need to keep in mind that it almost certainly is not a half. Huge mistake that very often is made is simply saying, well, below a half is negative and above a half is positive. That's rarely the case. We won't see it at all in any of our examples. So the best t for many applications is the one that gets the best receiver operating characteristic score. So we'll look at ft points with a subscript of the actual threshold. So here's some points just to illustrate. Notice that t equals 0 means we have extremely positive. Everything greater or equal to 0 is positive, which means everything. And extremely negative means nothing gets labeled as positive. The best t is the one that's closest to the ideal point. And usually we connect the dots with a curve that's parameterized by the thresholds. And then we can look at the area under this curve, and once again, it's the area under the receiver operating characteristic, the ROC curve. Therefore, it's the probability that a positive-negative pair is classified correctly. So let's look at some examples. So we've got 1,000 points, n equals 4. We're looking at our tunable binary data. A point xy is labeled positive if cosine squared of n pi x is greater than y, but our predictions are going to be confidences in that positivity. So here's our decision surface, and you can see from the color bar how the colors are to be interpreted. And here's our receiver operating characteristic. 97% area under the curve. And notice our best threshold is 0.6. Now let's suppose we went up to n equals 8. Our decision surface doesn't look nearly as good. We've lost some of the verticality detail. And not surprisingly, our receiver operating characteristic is not as good. The area under the curve is only 0.88. Notice once again, however, that our threshold is 0.6. What if we went to 11 neighbors instead of just 5, then now we're down to 0.82 for the area under the curve, and our threshold is 0.55. Now we're going to go up to 17. Notice our decision surface is practically a blur, and our area under the curve is dropped to 0.76, and our threshold is 0.53 for the optimal threshold. So the receiver operating characteristic is based on the fact that nearest neighbor methods make a prediction with only a few neighbors and not the entire training set. So as topologies become more complex, such as n gets larger in our tunable binary data, nearest neighbor methods become localized. So we see we're going to need better algorithms. However, we saw this visually, and it's not always possible to visualize, but we can always use the receiver operating characteristic to give us the same information that visualization does. So there's often an important question to address: do we need better algorithms or more data? The answer is almost always more data, and we'll confirm this using the receiver operating characteristic. So let's go back to 5 nearest neighbors. Now let's go up to, however, for n equals 8, 10,000 points. Notice our decision surface. We've recovered some of the detail that we lost with 1,000 points in n equals 8. And now the receiver operating characteristic is back up to a high area under the curve. And you can see from the raw data itself that the more data has given us the better results. So in theory, if we let A be the actual class and Y be the predicted class, then the total positives, or the true positives over the total, is essentially the probability that both Y is 1 and A is 1. And the false positives over the total is the probability that Y is 1 and A is 0. Similarly, for Y equals 0, A equals 0, that's the true negatives, and Y equals 0, A equals 1, that's equal to the false negatives over the total. So the true positive rate is the true positives over the total and P over the total. Therefore, it's the probability that Y is 1 and A is equal to 1 divided by the probability that A is equal to 1. That's actually what we would call a conditional probability. The probability that Y is 1 with the condition that it's actually 1. So the true positive rate is a conditional probability. Similarly, the false positive rate is a conditional probability. It's the probability that Y is equal to 1 given that the actual was 0. So that means we can use the receiver operating the ROC curve to compare two classifiers. So for a test point chosen at random, we look at the false positive rate and the true positive rate, and we can look at the two curves, and we can notice how the two curves, area under the curves, are related. Now, very often we do this using what's called the Gini index, which is 2 times the area under the curve minus 1. So the area under the curve is between 0 and 1. The Gini index is between -1 and 1. In both cases, the closer you are to 1, the better. So the ROC curve, it's a good tool for estimating how good a classifier is at predicting the class of an unlabeled observation. One thing that I'm going to leave for an exercise, that we really only ever use the ROC curve when the number of positives, actual positives, is approximately the same as the number of actual negatives. And I'll let you think about why it fails if that's not true. A good tool, the ROC curve is a good tool for comparing two classifiers for the same set of data. And it's a good tool for determining if you have enough data and if you're using that data effectively.